All right, greetings everyone. Welcome to the video for section 3.4. For all of you who have been waiting for finally some applications of this stuff we've been doing, here is your chance to get a taste of that. If you're tired of just talking about functions that don't seem to have any context, well, we'll get a little bit more into context in this today. The other thing I want to say is I really love this meme as a dog lover because the dog is the one on the top doing the rules correctly, whereas the cat on the bottom is the one not doing them correctly, although I say that with all due respect to you cat people who are watching, so apologies to you all. Okay, so we're going to look now at derivatives as rates of change, and this just means we're going to look at kind of how they relate to rates of change in applied problems. So let's look at this one. So we have a particle that moves along a straight line, and its position t seconds after it starts moving is given by the function s of t equals 2t cubed minus 24t squared plus 90t. And the position is given as a distance in feet from the particle's starting position. So just an example as a visual of what's going on. So let's say this right here is our starting position, and that's our particle. It's going to move along a straight line, and we'll just assume it's going to the right. And as it moves, after a certain amount of time, it'll be at some position along here. So if it's moving along, and then it ends up here, let's say after 3 seconds or whatever. Okay, so that is the kind of the situation that's going on here. And if we wanted to know what this position was after 3 seconds, well, we could just plug 3 in for t up here, and whatever we get out, that's the position. Okay, and the position is given as a distance from the starting point. Okay, so first things first, kind of a review of some stuff we've done before. They want us to find the particle's velocity at time t equals 2 seconds. Well, how do we do that? Well, you may recall from earlier in this unit that if we want to find velocity, the way we do that is we find the first derivative. So we'll take the first derivative of our function here. We can use the power rule to do that. So if we do that, we'll end up with 6t squared minus 48t plus 90. So that's our first derivative. That gives us velocity. If we want to know the velocity at the time t equals 2 seconds, how do we do that? Well, we simply just plug in 2 for t. So we do s prime of 2. Plug in 2 everywhere we see t and s prime. And I think if we do that, we end up with 18. And actually, let me rewrite that. Dang it. It's not what I meant to do. Write that a little bit smaller so I have some more room here. Okay, so s prime of 2 is 18. And what are the units here on this? Remember, our units for first derivative for velocity are based on the original function. And they'll be the output units, which are feet, per the input units, which are seconds. So this would be 18 feet per second. And then for the second part, we want to find the acceleration. And so remember, acceleration comes from taking the second derivative. So we'll do s double prime of t, which will give us 12t minus 48. And again, to find the acceleration at time 2, we can get s double prime of 2, which will give us negative 24. And what are the units here? Well, remember, they would be the output units for velocity, which are feet per second, per the input units for velocity, which are seconds, so feet per second per second. Or as we've talked about before, those just become feet per second squared. And notice it says that the acceleration is negative. So what does that mean if the acceleration is negative? Well, if the acceleration is positive, what's going on? Well, the thing is going faster, or its velocity is increasing. So if it's negative, that would mean the velocity is decreasing, is what it means if our acceleration is negative. Okay? Cool. So let's kind of review some stuff we did earlier. Let's take this a step further now. What now if I want to know when the particle stops moving? And first of all, they tell us here that the particle stops moving twice. so there are two different values where this happens. They want us to find those two values. We'll have to somehow use stuff we were just doing. Well, if the particle is not moving, what is its velocity? Well, the velocity would be equal to 0. So if we want to know when it stops moving, what that means is we may need to find out where the derivative, s prime, is equal to 0, right? And so what we'll do is we'll take our derivative function, which is 6t squared minus 48t plus 90, set that equal to 0. Now here we have a quadratic equal to 0, so there's a couple of different ways we could solve that. We could use the quadratic formula, or I noticed looking at this that all three of these terms here, let's see, they're all divisible by 3. I think they're all also divisible by 6. So I could factor a 6 out, so this becomes 6 times t squared minus 8t plus 15. And I think that this part now, this t squared minus 8t plus 15, that factors. And so this would become, and sorry, I'm running out of room. I'm going to have to erase this top part. So this would become 6 times, I think we'd get t minus 5 times t minus 3. Since negative 3 times negative 5 is positive 15, and negative 3 minus 5 is negative 8. And then from there, we know we can solve by just taking each of those pieces, the t minus 5 and the t minus 3, setting those equal to 0. And we find that in each case, we get t equals 5 and 3. And since those are values of t, what are the units on those? Those would be seconds. So we see here that the particle stops moving at the time t equals 5 seconds and time t equals 3 seconds. So there's two different places where that happens. Okay. All right. Now, a few different things they want us to do here. So first of all, they want us to find the particle's position at time t equals 13 seconds. So if we're just finding the position here, well, that's what our original function gives us. So we just need to do s of 13, so plug in 13 there, and if we do that, we get 1508, and the units on there, remember the outputs are feet, so that's 1508 feet. And they want us to know what, then they want us to figure out what the total distance is the particle travels between time t equals 0 seconds and time t equals 13 seconds. If we want to know how much distance it travels between those two, what might be some useful information to know? Well, first of all, we already know that after 13 seconds, we're at 1508 feet. What else might we want to know? We want to know the position at 0 seconds. So we plug in 0. And if we plug that into our function up there, we should get 0 feet, which hopefully makes sense. It's the starting position, right? And so if at 0 seconds we're at 0 feet, and then at 13 seconds we're at 1508 feet, it may make you think, well, to go from 0 feet to 1508 feet, we have to travel 1508 feet, right? And so there's our answer. And so you'd go home, feeling all happy with yourself, plug that into WAMAP, and you know what WAMAP would say? That is not correct. So what is going on here? Well, let's start with our picture again. And we had that spot where particle was starting, and then it was moving along a line to the right. And we know that starting point, that's when t equals 0. So that's at 0 feet. We just found that after 13 seconds, it's at 1508 feet. And then we also found a couple of other important points, right? We also found 2 points where the particle stopped moving. So the first one we saw was at 3 seconds. Okay, and then the other one was at 5 seconds, and I'm going to hold on for a second before I put the 5 seconds on there. Let's find the particle's position after 3 seconds. So that means we do S of 3. Now if we plug that in to the function, we'll get 108. So we know that the particle is at 108 feet after 3 seconds. I also realized I wrote this down wrong. So this should have been t equals 13. It's at 1508. And then we also know that the particle stopped at 5 seconds. So let's look and see what we find if it's the position it's at after 5 seconds. So if I plug in S of 5, you'll see I get 100 feet. Now, how is that possible? If at S of 3, so after 3 seconds, we're at 108 feet, how after 5 seconds could we be at 100 feet? What had to happen? Well, hopefully the conclusion you get is that the particle had to move backwards, right? So it had to go back to be at 100 feet. Okay? So what I'm going to do, because this is getting really messy and it's really hard to see, I'm going to clear this out, and I'm going to change to this whiteboard here and draw a better picture of what's going on. So here we started here at t equals 0 seconds. We have our line out to 13 seconds. Right, so this is t equals 1. This is t equals 13. We saw that at t equals 3 here, we're at 108 feet. So that's at t equals 3, we're at 108. At 0, we were at 0. At 13 seconds, we were at 1508 feet. Okay, and then we saw after 5 seconds, we had moved back to 100 feet. Okay, now how are we going to find the total distance we've traveled? Well, let's check this out. So from t equals, and I put t equals 1, that should say t equals 0. At t equals 0 feet, or t equals 0 seconds, we were at 0 feet, and we traveled to 108 after 3 seconds. So that's 108 feet we traveled. And then from 3 seconds to 5 seconds, we actually went back to 100. So how far did we go there? Well, that would be a distance of 8 feet. And then from t equals 5 seconds to t equals 13, we went from 100 feet to 1508 feet. Which, how far is that? Well, that's 1408 feet. And adding all of those together, it looks like we come together at 1,524 feet as the total distance we traveled. Now, that's different than our displacement after 13 seconds. So when you get into physics, or for those of you who've taken physics, our displacement was 1508 feet because we went from 0 feet to 1508 feet. That was kind of like our net gain. But to get that far, we actually had to walk or move a total of 1,524 feet with the stopping and moving backwards and then moving forwards. Okay? Cool. All right, let's go back to the PowerPoint then. Okay, so that's for that one. Before we do our next two problems, we're going to talk about something called marginal cost. So let C of x be a function that describes the total cost a company incurs in producing X units of a certain commodity. So if you can imagine something like a company like Apple, they want to know if they want to produce 1,000 iPhones, how much that costs. Well, they'd have a cost function where they could plug in 1,000 and it would tell them how much it costs to produce 1,000 iPhones. Then the instantaneous rate of change of costs with respect to the number of items produced given by the function c prime of x is called the marginal cost. So if we're looking at basically the derivative, trying to find the rate of change of a particular cost at a particular production level, then that would be our c prime of x, or our marginal cost. Okay, and I'll talk more about that when we get to the problem that relates to this. Before we do that, you guys may have been wondering, it's been a while since we've done something with Queen Beyonce, so don't worry, she is back. So the number of people, P, present at one of Queen Beyonce's concerts, T hours after the door open, is given by the function P equals negative 10,000 T squared plus 60,000 T. And what we're asked to do is to first find the rate at which people are entering the concert 2.5 hours after the door opens. Okay. Well, as we were talking about in the last problem, we need to find a rate of change here. And in order to do that, we need to find the derivative, right? So the first thing we need to do here is take P prime, and using our power rule, that's going to be negative 20,000 T plus 60,000. And then if we want to know the rate at which people are entering after 2.5 hours, well, we'll just evaluate that at 2.5. So plug in 2.5 for T. And when we do that, it looks like we get 10,000. And let's also figure out the units there. So remember, the units for the derivative come from the output units per the input units from the original function. So our output was number of people. Our input was hours. So the units here should be people per hour. Now, to be clear, that doesn't necessarily mean that after 2.5 hours, 10,000 people were coming in, or after even an hour, 10,000 people were coming in. That just means that after 2.5 hours, at that moment, when if we were to measure the rate at which people were coming in, that would be at a rate of 10,000 people per hour, which seems fairly high. Okay, so it probably means a lot of people are coming in at that point. Okay, and then we're asked to figure out at what time people stop entering the concert. So if they're not if they're stopping entering the concert, what is the rate of flow or the rate of change of people entering? Well, that would be 0, which means we could take our function and set it equal to 0, or our derivative here. So we'd have 0 equals negative 20,000 T plus 60,000. And if we solve that, we end up with T equals 3, and these are be hours because they're T values. Okay, so it looks like that is when that flow is now 0, no more people are coming in. That's about 3 hours. So this 2.5 we had down here, that was pretty close to peak entrance time, which I don't even know why someone would wait 3 hours to go to a Beyonce concert, but that's not our topic for this class. All right, now let's look at a marginal cost problem. So here we're told that the cost C in dollars of producing X books is given by C of X equals X squared over X plus 3 plus 10. Again, to explain what that means, right? If we want to know what the cost was for producing 1,000 books, we could plug in 1,000 for X here, and the number we get out would tell us what that cost was. Now here we want to find the marginal cost at what's called a production level of X equals 7 books. So basically we want to see what is the rate of change of the cost at when we are producing 7 books. So if we're going to do that, first of all, we need to take the derivative. So we need to do C prime of X. And notice we have two pieces here, the X squared over X plus 3 and the 10. That X squared over X plus 3, we have two functions being divided there, which tells us we use our quotient rule on that one. If you do that, you can double check this, but I believe you'll get X squared plus 6X over X plus 3 squared. And then if we take the derivative of the 10, that's a constant, so it just becomes 0 and it goes away. And if we want to know our marginal cost now at a production level of X equals 7 books, well, all we need to do is plug in that 7. So we'll do C prime of 7, which will give us 7 squared plus 6 times 7 divided by 7 plus 3 squared. And if we work that out, it comes out to be 0.91. And we'll use our units here to figure out what that means. So first of all, the units for the outputs per the inputs from the original function, so it'll be dollars per number of books. So it looks like this is 91 cents per book. And again, what that means is that the cost is changing by 91 cents per book when we produce 7 books. Now, I'll admit to you guys, this type of problem is not necessarily my expertise, but for any of you studying business or econ, you may have seen something like this before, and or you could ask your business or econ professors about it. All right, that's all I have for now. Thank you for watching.